Good morning, students. Today's topic is AVL trees. AVL trees is nothing but it's also a binary tree. It also a binary search tree. That means it satisfies the binary tree condition and it also satisfies the binary search tree condition. What's binary tree? Binary tree is nothing but at most two children. At most two children. In a tree, every node having at most two children is called as a binary tree. What is binary search tree? Binary search tree is nothing but every root node, when compared to root node, what the nodes are having the less than the root node, that nodes are placed in left side, greater than the root node, that placed at right side. Okay, that's the binary search tree. So these two conditions can satisfy in AVL trees. Okay, so then it is a self-balanced binary search tree. Okay, for that here AVL trees is a self-balancing binary search trees. AVL trees is a self-balancing binary search trees. Okay, and then self-balancing here, self-balancing. Before discussing about the self-balancing, which way we get the AVL? AVL means what? Means AVL is nothing but Adelson, Velsky, Lindzen. These three scientists find out the AVL trees. For that, for the remembering of the scientist names, they keep like as a first name of AVL. AVL trees. In the year of 1962. In the year of 1962, 1962, AVL tree can find out by the scientist of Adelson, Velsky, Lindsay. Okay, okay. For the remember purpose only, they give the name AVL. Okay, and then self-balancing binary search tree. AVL trees is nothing but self-balancing binary search tree. What is balancing? Self-balancing. Balancing is nothing but self-balancing is nothing but balancing the heights of left and right subtrees in a tree. Balancing the heights of left and right subtrees. Okay, balancing heights, and actually in a tree, which way we can balance the left and right subtrees of heights? Okay, which way we can balancing heights can be measured by using the balancing factor. Balancing heights can be measured by using the balancing factor. Balancing factor means is nothing but height of the left subtree minus height of the right subtree. That means the differences between the height of the left subtree and height of the right subtree. Left subtree minus right subtree. That is nothing but balancing factor. Okay, no confusion at all. Here AVL trees is a self-balancing binary search trees. Self-balancing binary search trees is nothing but balancing the heights of left and right subtrees. By which way we can balance the height of left and right subtrees? Here by using the balancing factor. Balancing factor is nothing but the differences between the height of the left subtree minus height of the right subtree, which can be either when you are find out the balancing factors, we get the results like this: 0, 1, minus 1. Most probably you get the results as a 0, 1, minus 1. Every node should satisfy the balancing factor of 0, 1, minus 1. If you get 0, 1, minus 1, it is a AVL tree. If you suppose you get the more than 1 or more than minus 1, then it is not a AVL tree. It should not satisfy the AVL tree condition. Okay, then here height is nothing but longest path from leaf node to that node. Height is nothing but, suppose if you take this node from this node to leaf node, how many levels we have? 1, 2. Okay, 2 levels. Then height of the left subtree is 2. Height of the right subtree is except the root node, height of the right subtree is 1. Okay, like this way we can find out the balancing factor. Here AVL trees is a balancing factor. I will take one example here. Root node is 80. Root node is 80 and then here left side I have 50. That means compared to 80, 50 is less. So I kept in left side. 100 is greater. So right side 50 and then here also 40 and then here also 60. It satisfies the binary tree as well as binary search tree. So it is a AVL binary search tree. Then it satisfies the balancing factors also. Balancing factors are 0, 1, minus 1. These are the balancing factors. Here, which way we can find out the balancing factor? The differences between the height of the left subtree and then height of the right subtree. Height of the left subtree is, except the root node, how many heights we have? 1, 2. 2 levels. And then here, height of the left subtree is 2. Right subtree is how many levels? 1 level only. Here 1. 2 minus 1 is 1. Okay. 1 you get the here. And then I will take another example here. Here 80, 50, 40, 60 and then 30, 25 and then 20, 25. Here 100. It satisfies the binary search tree condition and then binary tree. But here height of the left subtree. What? Height of the how many levels you have? 1, 2, 3, 4 levels. Okay, except the root node. This is the root node. Except the root node. How many levels? This is the first level. This is the second level. This is the third level. This is the fourth level. Height of the left subtree is 4. Which way we can find out the balancing factor? That means BF we have find out which way? LST minus RST. Height of the left subtree minus RST. Right subtree. How many levels in right side? Only 1. Okay, 1. That means 4 minus 1 is 3. This satisfies the balancing factors. Which what the balancing factors are? You have 1, 0, 1, minus 1. This 3 is belongs to 0, 1, minus 1? Not, no. So, it's not a AVL tree. Okay. And then, if the balancing factor, after find outing the balancing factor, you get, if suppose minus 1 is, this tree is called as a right heavy or heavy right AVL tree. That tree we can call as a right heavy or heavy right AVL tree. Suppose if the balancing factor is 0, then it is a balancing AVL tree. Then it is a balancing AVL tree. Suppose if the balancing factor is 1, then it is called as a heavy left AVL tree or left heavy tree. Here in this example I get the 1 only, no? 1. 1 means what? Here, if the balancing factor is 1, then it is called as a heavy left AVL tree. So, this tree how you call? Heavy left AVL tree. Heavy left AVL tree. Okay. Then, I will take another example here. This the height of the thing is 2 and this is 1. So, 2 minus 1 here, heavy AVL tree. Suppose here is another example I take here 80, 50, 100, 90, 120. Here height of the left is 1, height of the right is 2. 1 minus 2, what the balancing factor you get? Minus 1. Then it is called as a right heavy AVL tree or heavy right AVL tree. And then next one. Here, I will take another example here, 80, 50, 100 and then 40, 60 and 90, 20. Height of the, except the root node, balancing factor, first of all, you have to find out every node. In a tree, every node must satisfies the balancing factor. Then only you can tell it is the AVL tree. Okay. Here, balancing factor. Find out the balancing factor. What the height of left subtree? 2. And what the height of right subtree? 2. 2 minus 2, 0. If the balancing factor is 0, then it is called as the tree what we call? AVL balancing tree. Balancing AVL tree. Balancing AVL tree. Okay. And then every node should satisfy the balancing factor. Suppose this is the root node. How many levels you have? 2 here 2 levels, this is the 2 levels, that means 2 minus 2, what? 0. And then this one, 50 is the root node, and then how many levels we have right and left? 1, 1, that means 1 minus 1, 0. Okay, and then 100 also 1 minus 1. Balancing factor, which way we can find out? Height of the left subtree, height of the right subtree. What the height of this? 1. What the height of this for 100? For to right, 1. 1 minus 1, 0. Every node having this 0. And then here also there is nothing, 0, 0, 0. This is the overall AVL tree. Every node should satisfy the balancing factor. Okay, and then here also perform some operation like as a binary search tree. Whatever the operations we are performed in binary search tree, that same operations here also we are performing. What the operations you have? Insertion, deletion and search operation. And then here for insertion are also same way as a binary search tree. Whatever the insertion thing you have to listened in last class in binary search tree, the same procedure here also we have to follow. But one thing is here we should satisfy the balancing factors. AVL tree property. AVL tree property, what the property having? Balancing factor. Every node, whenever you are inserting the nodes in a tree, then we should satisfy the AVL balancing property. It can be balanced when if suppose it can't be balanced in one of the position, we have to apply some rotations. Have some rotations. What the rotations are? LL rotation, and then RR rotation, and then LR rotation, and then RL rotation. LL rotation means left side left only. RR means right side right only. LR left right left. These all the rotations we have, but we can't discuss it this in this video. And then this is enough for related to your syllabus. No need to this all rotations. And then like that here also deletion operation also same as a binary search tree, but deletion may also disturb the tree of balancing of the. Suppose here I having the balancing AVL tree. Suppose I want to delete the 120, then it disturbs the balancing factor, no? Here a node having here what the balancing factor of 100, here the height of the tree is 1, and then here there is nothing. Why? Here I delete the 120, then 1 minus 0 means what? 1. Though the balancing factor also changes. So whenever you delete the element in a tree, then it varies the balancing factors of that tree. So sometimes it's not balanced. For that purpose also we are performed some rotations like whatever the rotations here performed in insertion, that all rotations here also perform. And then here every algorithm, search, deletion, insertion, having some algorithms. For algorithms having the average case and worst case, time complexities are same. In AVL tree all are having the same worst case and average case of time complexity is same. O of log n. Search, in search operation average case is O of log n, worst case also O of log n. Insertion also order of a log n, and then O of log n. Deletion also O of log n, O of log n. This is brief note about AVL tree. This is enough for your syllabus. Thank you for students.